Alright, so before we move on to the next lecture, I want to show you a couple of things with Maple related to Bessel equations and Bessel functions. Some of the stuff actually I'm going to start with will ask you to remember a couple of things from the theory of linear equations that you learn in Math 270 or the ordinary differential equation class. So as I mentioned in the previous part of the lecture, a Bessel equation of order n is this second order ODE, homogeneous ODE, linear homogeneous ODE with this standard format. So it has a very specific format. It's called order n because of this constant term here that appears in this parenthesis multiplied by y of x. So once again, there are Bessel equations are more general than this in the sense that n doesn't have to be an integer, but for our purposes we're going to stick to Bessel equations of order n where n is a natural number. So n can be 0, 1, 2, 3 and so on. Now, before I go into more details about the solutions of these differential equations, I want to point out that you learn from Math 270. I mean, you learn in the math in the course of ordinary differential equations that any linear homogeneous ODE of second order has the solution given as a linear combination of two independent solutions. So I want you to remember that, let me write it here actually in the text mode. For a second order, again, second order and homogeneous linear ODE, you would expect the solution to be in the form of some constant c1 times y1 plus some other constant c2 times y2, where y1, y2 are the two independent solutions. So, of course, in that class, you dealt with primarily with second order ODEs with constant coefficients. So we didn't have x terms that depended on x, right, as coefficients of y double prime, y prime, and y. You only had constant coefficients, and in that case, the solution was very easy to obtain from the characteristic equation. As soon as you have these coefficients dependent on x, remember, things can get tricky. Not so much in the case of the Cauchy-Euler equation, which is pretty easy to solve, okay? I mean, very similar in terms of difficulty to the case of constant coefficients, but as you'll see in this case, the solution is far more complicated. And not only is far more complicated, but in fact, the solution of this type of ODE, this so-called Bessel equation, cannot be actually obtained in terms of elementary functions. So, as you are already used to in this class, if one fails to find a solution in the closed form, I mean in terms of elementary functions, one can look for a solution in a series form. So basically you take a series representation, namely a power series in this case, as you will see, and then try to find a solution in that form. We're not going to go too deep into how this solution is obtained. I just want to point out that what we call a Bessel function is essentially a solution of this ODE. One of the two independent solutions of this ODE is the Bessel function, and it is obtained in a series form. If you look in the textbook, it explains a little bit how this is done. You take the solution in a power series form, and then you plug it into the ODE, and you try to obtain some sort of recurrence on the coefficients of that series, which will allow you eventually to find those coefficients. So let me actually run the system here with Maple just to see that Maple actually recognizes that this is a second order ODE, and it recognizes as being this particular Bessel equation, and it will give you the solution as a linear combination of two independent solutions. So let's first run the system with or the equation without any specified value for n. So I'm not gonna click yet on a specific value for n. So notice the solution is given as a linear combination of two special functions. Remember in Maple, if the function name is in non-italic format, that typically means it's a predefined function in Maple. So Bessel j n comma x, that means basically the Bessel function of order n. And the other one is called Bessel y n x, okay? So the first part, the first component of the solution is denoted by J, the other one by Y. Again, there shouldn't be any surprise that there's two independent solutions. That is true for any second order linear homogeneous ODE. Both of them are in a series format, basically. The one obtains, like I said, this one, Jn of x, in terms of a power series. The second one is obtained via a process called variation of parameters, and there is actually a homework problem which kind of explains how one obtained the second independent solution. So we're not going to go over the derivation of these coefficients of this power series. We're just going to provide it right away. And here, this series from 0 to infinity constitutes this part of the solution. So the so-called Bessel function of the first kind. So the first part of the solution, this one is called the Bessel function of the first kind. The second part is, well, guess what? Bessel function of the second kind. The Bessel function of the first kind will be the most important one for our purposes, as I will explain immediately. So once again, Bessel Jn comma x in Maple is essentially a notation for this series. Let's run actually the system for a specific value of 4 of n. So for example, if n is equal to 4, you will notice that the solution is given in the same format, but now n is replaced by 4. And if I run Maple for this series, you will get again Bessel function for x. I mean the Bessel function of the first kind of order 4. So this thing is exactly this series. Fortunately, you will see that you're not going to need to work directly with this series because it will be very tedious. If you notice here, the coefficients of this series are quite tedious, right? I mean, they involve factorials and some powers of x over 2. If you want to see a couple of first terms of this series, let's see if I want to see the first 5 or 6 terms. This is how it looks like for the Bessel function of the first kind of order 4. So just a power series with these complicated coefficients. Once again, these coefficients don't come out of the blue. They just come from imposing a series format for the solution and essentially plug it in that series in the equation and matching the coefficients and finding a recurrence and then finding these coefficients, and they happen to have these values. One important thing I want to mention at this point is that the reason we don't bother in this class too much with the Bessel function of the second kind is because in the context of the boundary value problems, you will notice that a condition that comes from the physical requirements of the problem will impose this constant C2 to be 0. So when we build up the solution by solving the Sturm-Liouville problem, one of the conditions will be actually a continuity condition of the solution, and as it happens, the Bessel function of the second kind is discontinuous at 0, and therefore one of the conditions will be that this constant C2 will be 0. So let's actually illustrate why that's the case. Let's plot the Bessel functions of the second kind, okay, so this part of the solution for various values of n. So for example, if n is 0, notice that near 0, the solution has a vertical asymptote. So as x approaches 0, the Bessel function of the second kind is discontinuous and goes to minus infinity. This is true for any order. So if I replace n with 1, 2, 3, 4, and so on, again, the zeros of the functions may change, the overall shape it may change, but all of them are discontinuous at 0. Now remember that one motivation for dealing with Bessel equations was to solve the heat equation in a in cylindrical coordinates. So the domain, remember, was usually for the radius was 0 and 0, okay? I mean, so the radius was a positive number. The domain for this equation was some interval from 0 to some specific number, which denotes the radius of that cylinder. For the problem to make sense from a physical perspective, the temperature should have a finite value at all points, including at 0. So whether the function is defined at 0 or not, we should have, basically the function should be, it should be not only defined, but it should be continuous at that point and have obviously a finite value for the temperature. So for that reason, one automatic condition on the solution when we solve the Sturm-Liouville problem is to impose this constant to be 0. So therefore, we're not going to deal with the Bessel function of the second kind. Because again, its coefficient in the solution will always be 0 because of these continuity assumptions that come from physical properties of the problem. Another thing I want to mention at this point, let's actually see how the graph looks like for the Bessel function of the first kind. So let's replace y with j. So now we're going to plot this. And let's plot this function for various values of x, for various values of n, sorry. So notice that this is indeed continuous in the interval 0 infinity, and as you can see, it will have infinitely many zeros. So again, we can extend a little bit the domain here just to convince yourself that no matter how big the domain is for x, the function intersects the x-axis infinitely many times. Now, these zeros don't have exactly nice values. You could always approximate it with any degree of precision you want, but suffices for our purposes to know that these zeros exist. So whenever you set a Bessel function of the first kind equal to 0, you're guaranteed to have infinitely many positive roots. Okay, so, and they will be denoted, you will see in the lecture, as alpha 1, alpha 2, alpha 3, and so on and so forth. Again, these roots are not the same for various Bessel functions. So for example, if I change the order, let's say Bessel function of order 2, you could show that these zeros will be different, not the same as when n was 0 or 1 and so on, but in all cases you will have infinitely many zeros on the positive semi-axis. This will be important to remember because at some point when we solve the Sturm-Liouville problem, this is where the eigenvalues will come from. Just like in the previous eigenvalue problems when we set up sine of something equal to 0 and we had, because of the periodicity of sine, infinitely many zeros, which were our eigenvalues, in the same manner here you'll have infinitely many zeros coming from knowing that there are infinitely many zeros for the Bessel function. By the way, if you don't believe me that this series is exactly the one, the Bessel function itself on the top, let's replace here 5 with infinity, and so notice that Maple knows already that this series is the Bessel function of order 4 of the first kind. So once again, fortunately, with the exception of maybe 1 or 2 problems in the beginning, we're not gonna deal directly with this series because we can come up with some computation rules which will make our work much easier to do. We're going to have computation rules involving the Bessel function so that we don't have to carry over these ugly summations each time we have to manipulate the Bessel function in the actual problem. So, to summarize, the general solution of the Bessel equation of order n contains, as we know already for any second order homogeneous linear ODE, a linear combination of 2 special functions. One of them we don't care about that too much because its coefficient, when we impose the physical requirements of the problem, its coefficient will be 0. So essentially, we're going to deal with the solution in this form, in the form of the so-called Bessel function of the first kind. And that function has infinitely many zeros on the positive semi-axis. So I think that's it for today. You should run this Maple file. It's given actually in the Blackboard before you move on to the next lecture in the chapter.